All right. Now these are types of equations we've covered already. Single replacement. Elements by themselves replace some part of a compound that they're like, and you get a different element by itself and a compound. All right. Then in double replacement, you've got two-part compounds, and the front part's always exchanged with what's in the back. A goes to D, C goes to B, and the front part here always remains in the front. There is a subcategory of double replacement that you also have to recognize. And the subcategory, so this is actually part of double replacement, but it's in addition to double replacement. Okay, and this is called acid-base. And actually it's the simplest form of acid-base. And let's see, would that be, yeah, well, that's the simplest form of an acid-base type of formula, okay? So this would be Arrhenius acid-base. Arrhenius is the person who came up with, let's see, that's not pronounced, Arrhenius. Okay, this is the simplest form of acid-base we're talking about here, okay? So acids always have to have hydrogens on the front. Remember that? Yes? Okay. So I'm going to symbolize the acid as HA. Yes? Yep. Okay. A is the backside of the whatever's the hydrogens are attached to. That's the A. Okay. Now you might have more than one hydrogen, but there's at least going to be one hydrogen on the front of an acid. Okay. And in the Arrhenius simple acid-base definition, there's always a hydroxide on the back. Like there's a hydroxide right here in our homework. Okay? That's a hydroxide ion. All right? So we're going to symbolize that as BOH. All right? This is the base. So that's a general formula for an acid. And this is a general formula for a base in the Arrhenius system. Okay? Since this is also double replacement, so it's a subcategory of double replacement. This is a double replacement reaction. The hydrogen is always going to join up with the hydroxide. And so you always get this. And that is water. And so when the B part here, the front part of this compound, joins up with the back part of this compound, as happens with all double replacement reactions, you get Ba, okay? And that, by chemistry definition, is a type of salt. It's how chemists define what a salt is. All right? So this is a subcategory called acid-base. So if you, at this point now, we would always classify this equation as double replacement because it got two-part compounds that exchange places. Front of this goes to the back of that. Front of this goes to the back of that. Up here, I've also got a double replacement where the front part of this went with the back of that and made water, and the front of this went with the back part of this and made a type of salt. So this is not only double replacement, this one is double replacement and acid-base. Okay? And on the test, you have to recognize and classify this equation as both double replacement and acid-base. Is that clear to everybody? This is not. It's not enough to say this is double replacement. If you claim it, if I ask you to classify it and you say it's double replacement, you get 50% on that question. You have to say this is both double replacement and acid-base. Does that make sense? Okay. Now, just so you know, acid-base can also be called neutralization. Because when you put acids with bases, it neutralizes the acid and neutralizes the base. Okay, so another way of stating this acid-base reaction is a neutralization reaction. All right? So we got a definition of a salt then. That's a new thing. Definition of a salt is the products in a chemical equation are always what's on the right-hand side. This side over here on the left-hand side, these are reactants. So on the right-hand side, the product of an Arrhenius, notice I'm capitalizing it because it's named for somebody, an Arrhenius acid-base reaction other than water. Okay? So if it's other than water, and this is the water, then this is the salt right here. Whatever you have that's not water in an Arrhenius acid-base reaction is the salt. Okay? Does that make sense to everybody? So when you say a reaction between an acid and a base always produces salt and water, that's only true if we're using the simplest acid-base definition called Arrhenius. Is everybody as clear as I can be with that? Okay? So let's give you another example then of a double replacement reaction that is also acid-base. Okay? All right. How do I know this is an acid? Hydrogen on the front tells you it's an acid, right? That's how we told you to recognize an acid formula, and we did so in the last unit when you had to name acids. Okay? You can recognize an acid because there's a hydrogen on the front. You name it like an acid by first naming it like an ionic compound, hydrogen phosphate. Since you have a polyatomic anion, you're going to drop the word hydrogen off the front and change the AT ending to IC. This is phosphoric acid. Okay, so we got an acid here. This is a base. Now, in an Arrhenius base, you always have hydroxide. An Arrhenius base always has hydroxide in the formula. An Arrhenius base always has hydroxide in the formula. Okay? An Arrhenius base always has hydroxide in the formula. So if the name of the compound is hydroxide, something hydroxide, that's an Arrhenius base. If it's some compound that has OH in it, usually on the back, that's an Arrhenius base. Okay? Alright, so we have an Arrhenius acid, got hydrogen on the front, got an Arrhenius base, hydroxide on the back. We have a potential double replacement reaction that is also acid-base, and that's the way you have to classify it on a test. So in a double replacement reaction, the front part of the first compound always joins up with the back part of the second compound. And we end up with HOH. These subscripts right here, this 3 and this 2, don't automatically travel. This 3 doesn't travel because it's not part of a polyatomic ion. This 2 is outside the parentheses. It is also not part of the polyatomic ion. The polyatomic ion is OH, has a negative charge. But the 2 is not part of that polyatomic ion. It's only counting the number of polyatomic ions you have. So this travels, that travels, but the subscripts don't. Okay? We're going to put the front part of this with the back part of that. Barium's going to join up with the phosphate. Okay? That subscript 4 is part of phosphate's formula. You look up phosphate on the polyatomic ion list or chart, the common ions list, and you'll see PO4 is phosphate. That's part of the polyatomic ion, so that 4 does travel. Okay? Subscripts only travel when they're part of a polyatomic ion's formula. Okay? You've got to remember that. Now, we got to balance these. I hope at this point you recognize that this is already balanced. Okay? We've been doing this enough that you should know that when you put hydrogen ions and hydroxide ions, you get HOH. Alright? But just in case, just to be consistent, hydrogen ions have a plus charge, hydroxide ions have a negative charge. You put them together, you need only one of these and one of these to neutralize the charges, so the formula is HOH. Barium, on the other hand, has a different kind of charge. You have to look it up on the periodic table of oxidation numbers in this class. If you're not in a class of this level, you should know that everything in the second column, and that includes barium, has a 2+ charge. So really all you have to know is where barium is to know that it has a 2+ charge. Barium has a 2+ charge. Phosphate's a polyatomic ion. You might need to memorize that charge in another class. In this class, we just look it up on a common ions list. And there's our phosphate right there, and it has a 3 negative charge. Okay? In an honors class, you'll be able to figure out where it is. Okay? Phosphorus is in the third column from the noble gases. 1, 2, 3. So a phosphide has a negative charge, and a phosphate ion and a phosphite ion all have 3 negative charges. Okay, that's just a pattern that I've shown my honors kids to help them figure it out because they have to memorize those. Okay, so how many bariums and how many phosphates do I need to balance this formula to make it neutral? Well, if I have if I have 2 BAs, that's going to have a 1+ charge. Let's see if we can go back and look at how we learned to do this back in the last unit, okay? In fact, I probably got some room down here at the bottom. Here's barium with a 2+ charge. Okay, go ahead. You're right. Phosphate. You're right. Okay, but let me, just because nobody else is answering but you, great that you've got it. Okay? Some people want to be shy and not speaking up. That's okay. But if you don't got it, let me show you how to get it. Alright? There's one way to do this. I can say I've got a 2+ and a 3 negative. And when I add those together, I get 2+ and 3 negative gives me 1 negative. Okay? So if I have 2 2+ charges and a 3 negative, I get 2 times 2+ is, and a 3 negative gives me a 1+. Alright, so I need some more negatives here. In the beginning I had some negatives, I added another positive here. Now I've got a positive, I need some more negatives. So if I got 2 times 2+ and 2 times 3 negative, that's a 4. That's a -6. What do I got now? -2. So I need some more positives. So now let's make it 3 times 2 positive and 2 times 3 negative. Now I've got a 6+ and a 6 negative, and that's what I want right there. That means I need 3 of the particle that has a 2+. So I need 3 barium because they have a 2 plus charge. And it means that I need 2 of the particle that has a 3 negative charge. So I need 2 of these phosphates. So when I put all that together into a formula now, I get barium, phosphate. I put a subscript 3 here to show I have 3 bariums bonded with the phosphates. And I put a 2 here outside of parentheses to show that I have 2 phosphates. So, this is a 3, and there's a 2. So we balance the formula. Do we have a driving force? How do we know? Well, not just a liquid, it's water. Okay, yeah, it actually could be a liquid, but the rule I've given you is you have to form either a solid or water. Okay, so this is water. It is going to be a liquid, so there's our driving force. We still need to know if this is going to be a solid or a liquid or aqueous. Okay, where do you figure that out? Well, not the activity series, right above it. Solubility rules, right. So find either barium or phosphate on the activity series then. Barium or phosphate on the activity series. We're not looking for sulfates, we're looking for phosphates. There's phosphates right there.
All carbonates and phosphates except for one of
Are
them
insoluble. So if there's water around, insoluble compounds are solids. The exceptions are group 1, barium's in group 2, and ammonium is definitely not ammonium. So this is not one of the exceptions, so this fits the all phosphates category. It's insoluble. Even when there's water around, it's still going to be a solid. Does that make sense? Okay. And now we're ready to balance the equation. List all your elements: hydrogen, phosphorus, oxygen, and barium. Make a grid. Count up all the hydrogens. I've got 3 hydrogens here. And I've got 2 hydrogens here. The 2 on the outside of the parentheses multiplies everything inside. So 2 hydrogens and 3 hydrogens is 5. I have 1 phosphorus. I have 4 oxygens here, plus 2 oxygens here, so I have 6 oxygens, and I have 1 barium on the left side. On the right side, I've got 2 hydrogens. I've got how many phosphoruses? There's 1 phosphorus in the polyatomic ion called phosphate. We're multiplying the phosphate by 2. That's 2 phosphoruses. All right, oxygens. This is a little more complex. I've got 1 oxygen here right now. And I have how many oxygens here? 8 of them. So right now I have 9 oxygens over here. Okay, how many bariums do I have? 3 bariums. Okay. All right, what do we save for last when we're balancing? Oxygen's last. What do we save next for next to last? Hydrogen. So we can either start with phosphorus or barium. Doesn't matter which one. Okay? Let's start with phosphorus. This is the first one here. You put a 2 in front of this formula here. That's correct. Okay? So to get 2 of these phosphoruses, I'll put a 2 here. But that's going to change the number of hydrogens, the number of phosphoruses, and the number of oxygens. Okay? Alright, so we have 3 hydrogens in the formula times 2. So that's 6 hydrogens right here, plus 2 here. So we currently have 8 hydrogens. Alright, we've got 2 phosphoruses, and the oxygens we're going to change. We have 4 oxygens in the phosphate of this formula, times 2, that's 8. Over here we have 2, so currently we have 10 oxygens. Okay? Alright, let's get our bariums fixed. Alright, we have 3 bariums on the right. How do I get 3 bariums on the left? Put a what in front of it? 3. All right, that's going to change the number of bariums, the number of oxygens, and the number of hydrogens. All right, we have 3 bariums. Okay, so we count all our oxygens next. I have 4 oxygens in the phosphate here, times 2. That's how many oxygens? 8. Over here, I've got 2 oxygens in the formula, or actually 1 oxygen in the hydroxide formula times 2. So that's 2 oxygens. Times 3, how many oxygens is that? 6. So that's 14 oxygens. Am I right? Okay. Now then, let's go back over here. Well, I think, did I put down the, I didn't fix the hydrogens yet, did I? Let's do that. All right, so I've got 2 times 3 hydrogens, that's 6. And I've got 2 hydrogens, because I have 1 hydrogen in a hydroxide, times 2. 2 hydrogens times 3, that's 6, right? It's 12 hydrogens. Okay. Now, phosphorus is balanced, barium is balanced. We save oxygen for last, hydrogen next to last. It's not time to balance the hydrogen. All right, how do I get 12 hydrogens here? 12 in front would give me 24 hydrogens, because I have 2 hydrogens in this formula here. I put a 6 in front of it. Okay, that'll change the hydrogens and the oxygens. Okay, so there's no hydrogens in this formula. We now have 12 hydrogens here. And let's do the oxygens. This is a little more complex. I've got 1 oxygen in the formula, times 6. That's 6 oxygens here, plus, and then I've got to figure out the number of oxygens over here. Got 4 in a phosphate, times 2, 8. That's 14. And it's all balanced out. Okay? Now, if I ask you to classify this reaction, it is double replacement, because the front part goes with the back part here, and the front part goes with the back part here, so it's double replacement. But we have an acid reacting with a base. We're forming water and a salt, so it's also acid-base. Does that make sense to everybody? Anybody have any questions about balancing formulas, predicting the products of double replacement and acid-basic reactions before I move on?